In Chapter 3, we are learning several new skills, particularly as it pertains to fraction notation and mixed numerals. But we will also apply some of the concepts we learned earlier about addition and subtraction, and multiplication and division, and also order of operations. So section 3.1 begins with least common multiples. And so here the idea is to find least common multiples, or LCMs, of two or more numbers. And that will be the main objective of section 3.1. So here we're looking at the definition of a least common multiple. And the reason why that's critical is because when we want to add or subtract fractions, the fractions must have the same common denominator. And if necessary, we find equivalent fractions using the least common denominator, the LCD, or least common multiple, also known as LCM, of the denominators. So that's the reason why the least common multiples are so important. Here's the definition of the least common multiple of the LCM. The LCM of two natural numbers is the smallest number that is a multiple of both numbers. Well, when you just read that statement, that might seem a little confusing. So let's look at an example. There are several different methods to find the LCM of two or more numbers. And one of them is to make a list of multiples. So here's how it works. When we are asked to find the LCM of 9 and 15, we make a list of multiples. So the multiples of 9 would be 9, 1 times 9 is 9, 2 times 9 is 18, 3 times 9 is 27, 4 times 9 is 36, 5 times 9 is 45, 6 times 9 is 54, 7 times 9 is 63, etc. So you get the idea. Now when we look at multiples of 15, of course 1 times 15 is 15, 2 times 15 is 30, 3 times 15 is 45, 4 times 15 is 60, 5 times 15 is 75, etc. So then we look for the smallest numbers, the smallest number, that's a multiple of both numbers, and of course that's 45. In other words, 45 is the smallest number into which we can divide 9 and 15 without a remainder. So that's the LCM in this case. So the least common multiple is 45. That's one way of doing it, and we'll discuss some other methods. So here's the explanation, method number 1. Find the LCM of a set of numbers using a list of multiples. Determine whether the largest number is a multiple of the others. If it is, that is the LCM. And we look at an example of this in a moment. That is, if the largest number has the others as factors, the LCM is that number. Again, that seems a little bit confusing when you just read it, but when we look at an example, you get the point. I will point out, that's part A or part B. Now, if that's not the case, check multiples of the largest numbers until you get one that is a multiple of each of the other numbers. So we'll be doing that a few times, and then you get the idea how to do that. So, using the list of multiples, find the LCM for 10 and 15. Again, we write multiples of 10, 10, 20, 30, 40, 50, etc. And then we write multiples of 15, 15, 30, 45, 60, etc. And so here we notice that 30 is the number, it's the smallest number that has both 10 and 15 as a factor. So therefore, in this case, 30 is the LCM. For the other example, number 3, again we write multiples of 6 and 8. So multiple of 6 would be 6, 12, 18, 24, 30, 36, etc. A multiple of 8 would be 8, 16, 24, 32, etc. And so here we notice that 24 is the smallest number for which both 6 and 8 is a factor. So therefore the LCM for these two numbers is 24. So it's a pretty simple procedure how we find the LCM. All right, so let's look at number 4. So here we notice that 10 is a multiple of 5. So that's part A, where it says determine whether the largest number is a multiple of the other. So 10 is a multiple of 5. 2 times 5 is 10. So therefore the LCM is 10. 1 times 10 is 10, and 2 times 5 is 10. So 10 is the LCM. Okay, for number 5, we have 3 numbers. So here we write multiples of each of the numbers. Now we already know that 80 is a multiple of 20. 4 times 20 is 80. But that still leaves open 45. So we need to still write multiples of these numbers. So 20, 40, 60, 80, and then we have 100, 120, 140, etc. Now, if you look at this, you may want to think about the larger number because it gives us bigger steps. So when we multiple of 80, we've got 80, 160, 240, 320, 400, 480, 560, 640, 720, and 800. Let's see, now for sure 20 goes into any of these numbers. Okay, now we just need to write multiples of 45 to see which is the smallest number for which that applies to all 3. So multiples of 45 would be 45. So 90 to do that 3 times 45 is 135. 4 times 135 is 180. And so we keep on going. 225, 270, 315, 360, 405, 450, 495, 495, 500. 540, 585, 630, 675, 720, 765. So anyway, as you can see, it's kind of tedious to do that, but that's the only method we have right now. So anyway, so we look at this and we say, aha, 720, that's the smallest number, that's a multiple for both 80 and 45, and since 20 is a multiple of, since 80 is a multiple of 20 anyway, so the least common multiple for these three numbers then is 720. So if we kept pursuing this method, you can imagine that if the numbers were a little bit more inconvenient, or if there were like maybe 4 numbers, this is going to be a pretty lengthy task to find the least common multiple of, especially larger numbers. So fortunately, there's an abbreviated method to find the LCM using a set of numbers, to find the LCM of a set of numbers using prime factorizations. Remember, we practiced finding the prime factorization of a number. Well, we're going to apply it right here. And so we write the prime factorization of each number. And then the B part is we create a product using each prime factor the greatest number of times that it occurs in any one factorization. So what does that mean? Well, let's look at an example, and then you get the idea what's meant by that. So when we have the two numbers, 8 and 10, so the prime factorization of 8 is equal to 2 times 2 times 2, or 2 to the third power. And the prime factorization of 10 is 2 times 5. So the greatest number of times the factor 2 occurs is 3 times. So in other words, for the LCM, we now form the product. The LCM is a product of 2 times 2 times 2. And now this factor 2 already occurs 1 time, so already occurs, so we don't count that one again, because the greatest number of times 2 occurs is 3 times. But then there's a factor of 5. Well, that only occurs 1 time. That's the greatest number. The number 5 occurs as a factor. So this will be our LCM, and 2 times 2 times 2 is 8, times 5 is 40. So therefore the LCM for these two numbers is 40. Okay, let's look at the two numbers 32 and 54. So 32 we can write as the prime factorization is 2 times 2 times 2 times 2 times 2, or 2 to the 5th power. And 54 is equal to 2 times 3 times 3 times 3, or 2 times 3 to the 3rd. So then the LCM for the factor of 2, the greatest number of times is 5 times 2 to the 5th power. So it's 5 times 5 times 5. 2 times 2 times 2 times 2 times 2, 5 times. And then the factor of 3 occurs 3 times 3 times 3 times 3. And that is equal to 864. So that's the LCM for 32 and 54. And you can just imagine if we had used the very first method we've used, writing multiples of each number, how cumbersome that would have been to write multiples of 54 and then multiples of 32 and then find out the smallest number for both of these. So anyway, so the prime factorization is a very convenient way to find the LCM for a set of numbers. In the guided solution example, we have to find the LCM of 18 and 40. So we factor 18 as 2 times 3 times 3. And the prime factorization of 40 is 2 times 2 times 2 times 5. So consider the factor 2. The greatest number of times that 2 occurs in any one of the factorization is 3 times. Write 2 as a factor of 3 as a factor 3 times. Okay, now we're going to continue here. Now we consider the factor 3. The greatest number of times that the factor 3 occurs is 2 times. 3 times 3. Write 3 as a factor 2 times. So we have 2 times 2 times 2 from the previous consideration. Now we write the factor 3 2 times, 3 times 3. And then the other factor is 5. Consider the factor 5. The greatest number of times that 5 occurs in any one factorization is 1 time. You should write it out 1 time. Write 5 as a factor 1 time. So then it is 2 times 2 times 2 times 3 times 3 times 5. And so therefore the LCM is equal to, I guess it would be 8, would be 360. Okay, so again, the prime factorization makes it a lot easier to find the LCM. Okay, let's look at another example, number 9. Find the LCM of 24, 35, and 45. So what do we do here? Well, we write the prime factorization of 24, which is 2 times 2 times 2 times 3. And the prime factorization of 35 is 5 times 7. And the prime factorization of 45 is 3 times 3 times 5. So the factor 2, the greatest number of times, is 3 times. 2 times 2 times 2. So therefore the LCM is equal to 2 times 2 times 2. That's the factor of 2 occurs 3 times. That's the greatest number of times. The factor of 3 occurs twice, so the greatest number of times in this factorization here. So times 3 times 3. And the factor of 5, the greatest number of times occurs is 1 time only, so times 5. And the factor of 7 occurs only 1 time. It's the greatest number of times. So don't get confused that the factor of 5, for example, occurs twice, but in any one factorization, the greatest number of times it occurs is 1 time. So that's why 5 is there only 1 time. Times 7, and when you multiply that out, that is equal to 2,520. So that's the LCM for 24, 35, and 45. 2,520. And by the way, you can check your answer very easily, and you can divide, maybe take a calculator, divide 24 into 2,520, divide 35 into 2,520, and divide 45 into 2,520. And in each case, you get a whole number without a remainder. So in other words, that is the LCM. So finding the LCM of 4 and 9, the prime factorization of 4 is equal to 2 times 2, and the prime factorization of 9 is 3 times 3. So therefore the LCM is equal to the greatest number of times that the factor 2 occurs, and that's 2 times 2 times the greatest number of times the factor of 3 occurs, and that's 3 times 3, and that is equal to 36. So that is the LCM for the numbers 4 and 9. Very simple example. And for finding the LCM of 6 and 25, the prime factorization of 6 is equal to 2 times 3, and the prime factorization of 25 is equal to 5 times 5. So therefore the LCM is equal to 2 times 3. 2 occurs once, 3 occurs once as a factor, and 5 occurs twice. So times 5 times 5, and that's equal to 150. So 150 is the LCM here, and the LCM for these two numbers was 36. For the previous example. So there you have it. And let's look at a couple other examples here. So for 3 and 18, well, we see right away that 3 is a factor of 18, so therefore the LCM is 18. 3 divides into 18, so that's the LCM. And for the next two numbers, 12 and 24, well, 12 goes into 24 twice, so therefore the LCM is 24. A couple of easy examples. Again, remember when we looked at the LCM of two numbers, we first look and see if one number divides into the second one. And then that would be the LCM. In the next exercise, we are asked to find the LCM of 24, 35, and 45 using exponents. So here's the idea. When we write the prime factorization of 24, it is equal to 2 times 2 times 3. And if we use exponents, so it would be 2 to the third times 3 to the first power. And the prime factorization of 35 is equal to 5 times 7, or 5 to the first power times 7 to the first power. And the prime factorization of 45 is equal to 3 times 3 times 5, or 3 to the second power times 5 to the first power. So what they mean by using exponents, when you write it in exponential format, then it's very easy to see the greatest number a factor is used. So here the LCM, if we look at the factor of 2, well, it's 2 to the third. That's the greatest exponent here. And we look for the factor of 3, and that has the greatest exponent of 2, so times 3 to the second power. And 5 has only an exponent of 1, so 5 to the first power, and then the factor of 7 is only 1 as the greatest power, so therefore it's equal to 2,520, which is exactly the same least common factor we used, common multiple that we had for the same exercise when we did not use exponents, if you look back. So 2,520 when we look at the exponents. So that's the LCM. Then there's a third method to find the LCM, and that is using division by primes. First look for any prime that divides at least two of the numbers with no remainder. Then divide, bringing down any numbers not divisible by the prime. And then if you cannot find a prime that divides at least two of the numbers, then the LCM is a product of the numbers. Again, that sounds a bit mysterious when you first read it, but when you look at the example, which we'll do in a moment, then you see how it works, and then repeat the process until you can divide no more. That is, until there are no two numbers divisible by the same prime. You also may want to look at the book, which has a very good example about this. But let's look at an example. Okay, so in example number 16, we had to find the LCM for 81, 90, and 84 using division by primes. So we can divide at least two of the numbers by the number 2. So 81 we cannot divide by 2, we simply bring it down. We divide 90 by 2, that'll be 45. And we can divide 84 by 2, that'll be 42. Next, we use the prime factor of 3 because we can divide 81 by 3, which is 27. We can divide 45 by 3, which is 15. And we can divide 42 by 3, which is equal to 14. Now these two numbers are, of course, are divisible by 3, but 14 is not. So therefore we bring 14 down. So 27 divided by 3 is 9, and 15 divided by 3 is 5. And that's the end. Okay, there's no more prime factor that we can divide any of the numbers, any two numbers by. The only number that's divisible by prime factor is 4, but we need at least 2, so that's it. Therefore, the LCM is 2 times 3 times 3 times 9 times 5 times 14. So that's how you determine the prime factorization. So 2 times 3 times 3, 2 times 3 times 3 times 9 times 5 times 14, and that is equal to 11,340. So you may want to go over this again, or look at the textbook, which has other examples like it. And so it takes a little practice. Again, you begin by looking for at least two numbers that are divisible by one of the prime factors, like 2 or 3 or whatever number it might be. So in this case, we began with 2 because we have two even numbers here. They are divisible by 2, 45 and 42. And we leave 81 because 81 we cannot divide by 2. But now we have at least 2. In this case, all 3 are divisible by 3. So 27, 15, and 14. And so then each one of those, well, here we have 2 that are divisible by 3, which we do. 27 divided by 3 is 9, and 15 divided by 3 is 5. And we leave 14 alone because it's not divisible by 3. And then the LCM is simply the product of 2 times 3 times 3 times 9 times 5 times 14. In this case, it's 11,340. Let's use the division of primes to find the LCM for 24, 35, and 45. So we begin by writing down the numbers 24, 35, and 45. And then we notice that there are two numbers that are divisible by 3, and that's 24 and 45. So 3 would be one of our first prime factors, so that would be 24 divided by 3 is 8. And we leave 35 alone because 35 is not divisible by 3. And then 45 divided by 3 is 15. And so now we're looking for two numbers that have a prime factor, and so there would be 35 and 15. So the prime factor we can use here is 5. So we leave 8 alone because we cannot divide 8 by 5 without a remainder, so 8. And then 5 into 35 is 7, or 15 divided by 5 is 3. Now there's only one number that has a prime factorization. So we are done. So in other words, the LCM would be the product of 3 times 5 times 8 times 7 times 3. So 3 times 5 times 8 times 7 times 3, and that is 2,520. So that's how it's done. So they provide the answer here, 2,520. And again, for practice sake, I would suggest try it on your own, see if you can do this. So for the next exercise, number 18, we have defined the LCM for 12, 75, 80, and 120. So we begin the same way. We write down the numbers, 12, 75, 80, 120. So here we have many choices how to start, but let's say we begin with a prime factor of 2. So we could divide 12 by 2, which gives us a 6. 75 remains because it's not divisible by 2. 80 divided by 2 is 40. And 120 divided by 2 is 60. And again, we can use a prime factor of 2. 6 divided by 2 is 3. We leave 75 alone because we cannot divide 75 by 2. And 40 divided by 2 is 20. And 60 divided by 2 is 30. Now we can use a prime factor of 5. And we leave 3 the way it is because we cannot divide 3 by 5, so it's 3. 75 by 5 is 15. And 20 divided by 5 is 4. And 30 divided by 5 is 6. So then for this row of numbers, we can use a prime factor of 3. 3 divided by 3 is 1. 15 divided by 3 is 5. 4 we cannot divide by 3, so we leave it that way. And then 6 divided by 3 is equal to 2. And now for this row of numbers, we have 2 numbers for which we can use a prime factor of 2. 2 we cannot divide 1 by 2, so we leave that alone. And same for number 5. 5 we cannot divide 5 by 2, so we leave 5. And 4 divided by 2 is 2. And 2 divided by 2 is 1. Therefore, the prime factorization for these 4, the least common multiple of these 4 numbers is now the product of 2 times 2 times 5 times 3 times 2. So 2 times 2 times 5 times 3 times 2 times 1 times 5 times 2 times 1. And that is equal to 1,200. It's a product of these factors, 2 times 2 times 5 times 3 times 2 times 1 times 5 times 2 times 1. Now, we didn't really have to divide by 1, but I just did it for consistency's sake because 1 is a factor here. So anyway, that's the answer to this question here. 1,220 is the LCM. And this is the end of section 3.1.